Okay, so the last section in this chapter is going to be on relative motion analysis, and we're going to look at acceleration. We haven't done much with acceleration, but now we're going to look at the right equations for that. So let's start with this equation here. If you remember from previous sections, we have that if you have, say, a link here, right? And so then this is point A, and this is point B, right? So, and then this is connected to something else here, right? So it doesn't matter right now. So then we wrote that the velocity of B, okay, this point B, was the velocity of A plus the velocity of B relative to A, right? So then you have the translation part and the rotation part. So this is the equation that we wrote before. VV is equal to VA plus VB relative to A, right? So these are all vectors. And so now we want to take the derivative of this to get the acceleration. So we're going to take the derivative of this, the derivative here, and the derivative here, right? So now these two terms here, these are measured against a coordinate system that is fixed. Okay, so this is an xy fixed. This term here, this is measured against a coordinate system that is fixed to this point. So you can think of this term as if you have an ant sitting here, what does it look like? What does the ant look at when the ant sees this point moving? It's going to see this point rotating about A. So that's what that uh, term means here, right? So this is the acceleration measure about this point where you are looking at this and you're sitting at this point. So because this is anything that moves about this point is doing a rotation here, right? So then it's going to have a tangential and a normal component. And we know how to write those, right? So we know how to write those alpha r and omega square r, right? So we've seen those before. So let's look at how to write those graphically. So that's what is happening. This is the general motion here, right? So that general motion has an acceleration for point A and an acceleration for point B. Also have uh, angular velocity here and an angular acceleration. So we break the motion of this guy into a translation and a rotation. So now the translation, this point here is going to have the same acceleration, and this is key, right? And this point here also, because it's a translation, have the same acceleration as this point. So these 2 points have the same acceleration, and this thing is moving in a straight line for this portion of the motion. So the real acceleration of B is this one here. So this vector minus this vector gives me the acceleration that you would see if you're sitting at that point there, right? So for somebody sitting at that point there, what that's gonna look like is you're sitting here and this point is rotating about A. So it has an angular acceleration and an alpha acceleration. So then we can go ahead and write that the tangential acceleration is alpha cross r b relative to A, and the normal acceleration is omega squared rb relative to A. This is the basic equation that we're going to use in this section to solve problems. And so we're going to need this equation later on when we write Newton's equations. So this is the equation that we need to solve, that we need to use. The acceleration of a point B is the acceleration of a point A plus the rotation of B relative to A, which is this term here. So now let's look at some important tips to solve this. So typically you're going to have problems like this where you have links and things that move like that. So how do you choose your A, your B, and your C? Sometimes the problem will give you hints on how to do that, but typically you want to look at the points that you know the motion, how the motion is going to be. For instance, here we know that this is a pure rotation. AB is doing a pure rotation, so B is going to have a rotational motion. And we also know that C is constrained to move in this direction, so C is going to have a translation motion. So then you can start breaking the motion, right? So this is the one that has the complex motion. This is a pure rotation here. And here, then we can use that equation that we know to find one acceleration in terms of the other. So how do we solve this type of problem? So establish a coordinate system. It's nice to draw a picture, right, with where you have all the important kinematics properties, and in your picture you should indicate what is the acceleration, what is your point A and your point B, if you label them that way. What is the acceleration of A, the acceleration of B, angular velocity, angular acceleration, and what is the vector from A to B. So, and then you can write the accelerations. So this is the equation that you're going to write. You're going to write this in a vector equation, which is the easiest way to solve this type of problem. And typically you are going to solve for unknowns, which are going to be, in some cases, alpha and some other acceleration. You may have more unknowns. If you do that, you may need to use an alternative equation like the IC to help with the extra unknown that you have. So let's look at one example to see how this works. So here we have a typical example. This roller is going down, and so you have point A, and so it's giving an acceleration of 5 meters per second downwards and a velocity of 6 meters per second. And you are asked to find the angular acceleration and the acceleration of B at that instant. So what we are going to do is we're going to have three unknowns in this problem. We can write two equations from the acceleration, the x and y, and we need a third equation. We're going to use the IC to find that. To find the IC, well, remember this guy has a velocity going that way. This guy has a velocity going that way, so we can take these two lines. This is the IC, the point that intersects those two lines. And then we can use geometry to find the IC, so we know the velocity of A, so we can, and we know this distance here, right? So this is a 5, 4, 3 triangle, so we can find from there the angular acceleration, which is 2 radians per second. So we know the angular acceleration, so now the angular velocity. Sorry, I think I misspoke there. So we know the angular velocity now. So we need to find the angular acceleration and the acceleration of point B. So let's write the acceleration. So the acceleration of A is -5 in the J direction, right? And the acceleration of B, this is an unknown. This is what we want to find, and it's AB in the X direction, right? So now we can write our general equation. The acceleration of B is equal to the acceleration of A plus the rotational part, right? The rotational part is the tangential acceleration, which is this term here, is alpha cross RBA minus omega squared RBA. What is RBA? Position of B relative to A, so it would be this vector here. And you can see that that vector is what? Well, it'll be 3I minus 4J. That is your vector RBA, right? So now we can break this equation into components. So we have the acceleration of B that has only an X component here. Then we have the acceleration of A has only a Y component here. Then alpha cross RBA. RBA is this vector here, right? And alpha K, we're going to write this. We don't know alpha, right? So that's the tangential acceleration minus omega squared RBA, right? So then this we found in the previous slide. This was 2 radians per second, so that's 2x squared. And then this is RBA. So now we can do the algebra here and break this into components. So we rewrite this a little neater here. And finally, we get this equation. And then we have now, this is our final equation here, where these are basically two equations, one for the x and one for the y. So we can solve this using simple algebra. So we get the x equation and the y equation right there. This is x, this is y. And then finally we can solve for a, b, and alpha.